This is a tutorial to develop a queuing model using the process interaction worldview for a simple queuing system similar to Caffe Java that we've been studying in lecture. In lecture, we identified that there's two key processes that take place in this simulation. There's the main run process, which will run the Caffe operations. The main component of the run process is waiting for some inter-arrival period and then generating customers. Those customers will be launched as new processes where they request a server, wait for that service to become complete, and then release that server to the next customer who could be in the system. Now, to develop this example, we're going to be using the SIMPy and NumPy packages. So I'm going to first of all import the SIMPy package and import the NumPy package and refer to it as NP. The next thing we can start to do is to build up our SIMPy simulation environment. We can create the environment using the SIMPy library.environment. And then if we want to run just with nothing in it so far, just to see if it's working, we can tell for the environment to run until, let's say, run for 10 minutes or 10 time units. This script runs. It doesn't really do anything yet because we're going to be building up our simulation model. So the first thing we want to do is to build this run process. This will be the main process for generating customer arrivals in the cafe. Again, to define a process in SIMPy, we will use a generator. I'm going to call this generator the cafe run generator. The first argument that it's going to take is the SIMPy environment that it will be operating in. And this particular process will run continuously. So it enters a infinite loop where the loop keeps on looping until while true is true. And while it's looping, it's going to yield for a certain timeout period. So we're going to take the SIMPy environment and timeout for a certain period. And that timeout period we're going to pass in as a inter-arrival process generator. So just let's create a process generator real quick. Similar to before, we'll define a function, say generate inter-arrival. In this particular case, we can return a random variable from NumPy following, let's say, an exponential distribution. And let's say that the inter-arrival period or the inter-arrival rate is 3 customers per minute. Now again, in NumPy, it's exponential process generator. It uses a scale parameter instead of a rate parameter. So what we have to specify here is 1 over the rate parameter, or in this case, 1/3 for 3 customers per minute, or 1 customer, or yeah, 3 customers per minute as a rate parameter. So now in our main run process, while true, we want to wait for the next customer arrival. So we'll generate an inter-arrival period. And let's just say for fun that we'll right now print out the current time, environment.now, and then say a customer arrives, right? So the next thing we have to do is to add this process to the SIMPy environment. So we're going to take this environment, add a new process to consider, and the process that we want to run, the generator, is cafe run. And this cafe run generator also needs to know the SIMPy environment passed in as an argument. Okay, so just running this script, we can see that we have a number of customer arrivals. We can see printed out here the current time that the customer arrival happens, and then this message, customer arrives. Right. So the next thing that we can do is within our kind of master cafe run process is once a customer arrives, we can launch a new process to handle that customer event. So I'm going to here, still within the while loop, launch in the SIMPy environment a new process. This one will be called customer, using also passing in the customer environment. or sorry, the SIMPy environment. And just down below, define a new process generator for a customer, or sorry, a new generator passing in this environment. Now, from the customer's perspective, the first thing that they have to do is request the server. And this is a bit of a problem right now because we don't have a shared resource yet defined in the simulation. So let's create a new shared resource. So down here in our kind of simulation script, I'm going to define a shared resource servers. It's going to be a SIMPy resource. It's going to be using our SIMPy environment, and it'll have a capacity of 1 to start with. Now these servers, we will need to pass them into the cafe run process so that this process knows what are the servers that it can have access to. So I'm just adding that as an argument to the generator function. And then I'll also pass that in as an argument to the customer function. So now that the customer's generator can know what servers they have access to. So inside of the customer process, the first thing to do is to request a server. So with these servers, we want to request one of them, save that request as the variable request. We want to yield until that request gets satisfied. So yield request. And then we want to time out the process. Well, we want to yield a certain timeout period. That timeout is going to be we'll create a new generator for the service period. So let's fill in this generate service process generator. So up here, define a new function for generate service. And here we can return a random variable drawn from an exponential distribution with service rate, let's say 4. So 4 customers per minute can be served on average. So this customer process, just to recap, they request a server from this shared servers variable. They wait until the request gets satisfied, and then they wait for the service to get issued. So here we can just print out some more messages, print out the current time, say that this customer is being served, and after so just before this request is where the customer arrives. We already have a message up here that does that. And we can say down here, customer departs after they've received service. So here, just by running this script, we can see a listing of customer arrivals, customer being serviced, customer departs. We don't yet have the kind of identifiers to figure out which customer is actually being referred to. So let's add one more piece of information here. So when we're generating these customer arrival events, we're going to kind of give them each an identifier to allow the code to figure out which customer is actually arriving and being served and departing. So just for simplicity, I'm going to move this message for customer arrivals into the customer process. I'm going to define in the cafe run process a kind of a counter variable. I'm going to start it at 0, and then every time it runs through the loop, I'm going to add 1 to this counter variable, and I'm going to pass this counter variable into the customer generator as the second argument, and I'll refer to this as the customer number here. So now, for each time this customer process gets called, we can print out which number customer is being referred to. So here I'm using this bracket notation, which lets me format a string with some numeric information passed from variables very easily. So now the cafe runs. Every time it calls the customer process, it gives it a number for what number customer it is. That customer process will now use that information to print out more user-friendly messages. So now we can see exactly which customer is it that we're talking about in each of these cases. Customer 1 arrives at time 0.39. They start being served right away, and then they depart a short time later. Meanwhile, customer 2 arrives a little bit later, is being served and departs, and so on and so forth. So one of the couple of other improvements to the script, we can give a seeded random number value. So it can seed the random number generator first at time 0, so we get consistent results. Each time we run the simulation, we'll get the same values for all the properties. We may also be interested in recording some data, as I mentioned in the lecture slides. So let's say, for example, that we want to measure the amount of waiting time each customer experiences. So I can just create a new variable here, waiting time. I'm just going to make this a standard list here. This gets a little tricky if you're trying to modify variables inside of functions. The general rule is you can modify complex variables, but you can't override simple variables inside of functions. So if we treat this as a list, for example, we can append to the list inside of the function. But if we were treating this as a number that we keep incrementing to or adding to, we'd have to use a global variable inside of the function, which comes out in some of the later examples. So let's say if we do want to keep track of the total waiting time for these customers, right when the customer arrives, we can record their arrival time. So it's the environment.now. And right when they depart, we can record that depart time is environment.now. And then store in this wait time list, we can append the departure time minus the arrival time to record those values. So now if I rerun the simulation, take a look at this wait time list, I get a list of all of the values that the customers waited during the simulation. And I can use that to create some plots to show different features. So one of the plots in particular that we might be interested in is to plot a histogram of waiting times. So if I, for example, import the matplotlib.pyplot, refer to it as PLT, then I can generate some very easy plots to plot the histogram of the waiting time. Just give it some nice labels. Plot.xLabel is the waiting time in minutes. And the Y label of a histogram is number of the counts. How many number of customers. So if I run the script, I get a nice histogram showing that majority of the customers had a really short waiting time, looks like between 0 and a quarter of a minute, but there were some customers that did have to wait a longer period of time, closer to 2 minutes, to receive their orders. Now this is an example of an observation that makes sense it makes sense to make this observation for each customer. The waiting time each customer experiences it makes sense to record that for every customer. If we wanted to find other information, like the average queue length, we need to make those observations independent from the actual customer processes. So to make these, generally falls under the category of process monitoring. We have to make some slight adjustments to our script. So I'm just going to put these in line here. We need to create some new variables to store data. So I'm going to have a list to record the observation times and also a list to store the queue lengths at each of those observations times. And I'm going to create a new process to observe the simulation model. It's going to be using the same SIMPy environment, and it needs a reference to which shared resource do we want to observe in this case. And I'll pass those in as the servers. So in this case, this observe process will be happening continuously, kind of in the background of the simulation. So I can loop through this process or this generator while true. I want to make a new observation, append a new observation time of the current simulation environment time, and also append a new observation for the queue length, which is the servers. So in the SIMPy library, a shared resource has a property called queue, which is the list of all of the objects waiting for access to that service. And we can take the length of that queue to record the current queue length as our observation. And this particular, to make it this a process generator, to make this a generator, we need a yield command. In this case, let's yield to wait 1 minute between observations. So we'll time out the simulation environment for 1 minute between successive observations. So this observe process, we can add it into the SIMPy environment. Same way we launched this master cafe run process. We can launch a new process to observe the environment and those particular servers. So now when we run the simulation again, we'll have observation times that have been captured, and it's every minute, just exactly how we specified. It's at time 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we had changed this, for example, to observe every 30 seconds, we will get slightly different results. So our observation times now fall every 30 seconds instead of every minute. And we will also have data for our queue length observed at each of those observation times. Now, a nice thing about this is that we can plot, so we can start to plot this data. So I'll create a new step plot here. So these are kind of discrete observations. The x-axis, I want to have the observation times, and on the y-axis, I want to have the queue lengths that have been observed. And just to get the step plot to line up properly, I need to pass in the post instruction for the where parameter. Let's just see what this looks like so far. Needed to create a new figure here. Might as well, for good practice, create a new pyplot figure before the other plot as well. All right, so this is looking good. It looks like we had a no queue for the first couple of minutes of the simulation, and then the queue built up to 5 customers and then went back down to 0. Let's just add a couple of labels to this. So the x-axis is the time in minutes, and then the y-axis is the queue length. This particular shape, though, is really just a function of the particular random number seeds. So if we were to change this seed from 0 to 1, for example, we get a completely different picture of what the queue length looked like. So some of the challenges for using discrete event simulation is that, well, first you want to run a simulation for long enough to get the right parameters or to get the right long-term or steady state behavior. So if we do run this, for example, for not just 10 minutes, but for 100 minutes, we get a much longer history from which we can calculate variables of interest. The other thing, though, is that this particular history is unique to the random number seed that we selected. So it looks relatively different for 0 versus 1. So we may have to make repeated samples of particular parameters of interest for seed 0, 1, 2, 3, and so on, and then compare those resulting factors to each other to generate confidence intervals, for example,